In this question number 2, we have an ideal gas question. So I can imagine this being the start of the physical chemistry idea here. So the first part here, draw one line on the graph. And what do they expect us to do? The relationship should be for the same amount of an ideal gas. If we look at our graph, we have PV on the y-axis. So P times V there. We know that Boyle's law. So Boyle's law basically states that at constant temperature, pressure is inversely proportional to the volume of a gas. And this only happens at constant temperature. So a lot of students, in fact, they do physics, but they forgot that the relationship only holds true at constant temperature. You cannot just simply say that without the accompanying statement like that. Having said that, then PV is equal to constant. This is for an ideal gas. So we could see that for an ideal gas, PV equal to constant. That means it shouldn't change no matter how pressure changes, no matter how volume changes. PV is a constant. So by right, it should be just a straight line, a horizontal straight line, because PV equal to constant value. It doesn't change irrespective of the x-axis there. State and explained. So there's two parts to the question. The first part is stating, the second part is explaining. So there should be two bits to your answer. With reference to the graph, which of the temperature is the lowest temperature? We know that the assumption, the most important assumption of ideal gas is to do with negligible intermolecular forces. Negligible means minimal intermolecular forces. In terms of temperature, you want the temperature to be as high as possible so that the molecules are further apart, so that the particles are further apart, and then they exert very little intermolecular forces between them. When you have low temperature, your particles are closer together. So if your particles are closer together, your intermolecular forces will be stronger. If your intermolecular forces get stronger, we can imagine these being less ideal. And when they become less ideal, we can expect them to deviate the most between T1, T2, and T3. We can see that T1 deviates this much at this particular pressure, and then if I look at another one, T2 deviates around this much by the green color, and then T3 deviates by around this much. So in terms of the T1, T2, and T3, the greater the deviation, the less ideal it becomes. The lowest temperature means the particles will be closest together, intermolecular force would be the strongest, and therefore is the least ideal. The least ideal would be the red color one, because that is the that will be the one that deviate the most from the ideality assumption there. Okay, so T1 is going to be the lowest temperature based on what I have said. That is the one, the graph above. So you need to use the graph. The graph above shows the greatest deviation from ideality. The greatest deviation from ideality, consistent with, so I'm trying to explain now, consistent with stronger intermolecular forces. So I can't use IMF because there's abbreviation. So stronger intermolecular forces as a result of molecules being closer together or particles being closer together. I don't want to use the word molecule because we are not sure about what this one is. And this one is at lower temperature. The particles are closer together, and as such, stronger intermolecular forces, greatest deviation from ideality, as I have just explained earlier. Now explain your answer in terms with reference to intermolecular forces. It seems that I have actually done the next bit in this bit here. That was a bit strange because there was only one mark there. I think I can then use the second bit of the explanation, the consistent with stronger intermolecular forces for this second bit here. So let me just move my point around. So sometimes it's quite challenging, isn't it? Like you put your answer in one part and then you don't really have the chance to actually write in the next part again. So in terms of stating and explain the previous question, there was one, and there was just the greatest deviation from ideality, I guess, because then the next bit is talking about the intermolecular forces, and there's a result of the particles being closer together at lower temperature. All right, so on to the next question. So what do they want now? They want to state and explain, so first part and second part again, the effect of pressure on the extent to which a gas deviates from ideal behavior. So now this is on the effect of pressure. We can think about, like when you have a gas piston like that, and you have a certain particle like that, and then you allow the piston to move a little bit out, but your particles, you still have the same amount of particle inside. So as I allow the piston to be moved out, going from here to here, I can think about the pressure decreasing. So when the pressure decreases, we can see the volume occupied by the gas, which is the volume of the container, would actually increase going that way. And that is basically the Boyle's law, which is applicable at constant temperature. So we could imagine as the pressure, so using the graph, as the pressure increases, we can see that these are for a real gas at 3 different temperatures. Let's just look at the one where it's just one particular temperature. Let's just look at T3 for instance. So this is the one that deviates the least from the ideal gas. This must be the highest temperature. But even for the highest temperature, we can see that it still deviates from ideality, where PV equal to constant for an ideal gas. And that is because at low pressure, your particles are further apart and they exert minimal or negligible intermolecular forces. Therefore, they are more ideal at lower pressure. Whereas at higher pressure, you're squeezing the particles closer together by decreasing the volume in which they occupy the container in, and as they occupy a smaller volume, they get squeezed closer together, and therefore they will become less ideal as they exert greater degree of intermolecular force. And when they get less and less ideal, you can see this going further and further up as they deviate more and more away from ideality. This is in terms of the changes in pressure. So I can talk about as pressure increases. Probably going to explain first in terms of one of the other assumptions of ideal gas, which is to do with negligible volume, or they have zero volume considered relative to the container size. But as you increase the pressure, you're making the volume of the particle less and less negligible relative to the size of the container, the volume of the container. So as pressure increases, the particles become closer together, the particles occupy smaller volume of the container. They get squeezed closer together, they become closer together, and this is the bit where you talk about breaking the assumption. So therefore, they exert greater intermolecular forces or stronger intermolecular forces between the particles. And these are forces of attraction between the particles, and they become less and less negligible, and therefore they become less and less ideal. Therefore, less ideal at higher pressure. And as such, we could see a greater deviation from ideality as seen from the graph here. We see a greater deviation from the PV equal to constant ideality for an ideal gas there. So state and explain the effect of pressure on the extent, less ideal at higher pressure. So that was just a stating bit, and I've just explained it in terms of the negligible volume of the gas particle relative to the container being less negligible volume as a result of the particles being squeezed closer together. Also, that will result in a stronger intermolecular force as well. So basically, they become more ideal at low pressure and also at higher temperature there. Now we got a calculation question in this next part here. We have a flask filled with a volume of 100 cm cube. So that's going to be the volume of the container. So the volume of the container is going to be the same as the volume of the gas, because gas fills up the volume of the container. Now what do we have? We have another gas Y filling the flask, and we measure this at 26 degrees Celsius. Keep an eye out for this. When you have ideal gas equation, PV equal to nRT, PV equal to mass over mRRT, you want the MR there. The MR is going to be move up there and move the PV down there. You're going to get mRT because you keep the M, you keep the R, you keep the T. They got multiplied together and they get divided by PV, whereas 1 over MR, the MR move up there, PV move down there. This is the general expression here. We never memorize this. We think about this, and from this we can get this very easily. Now what is very important is the temperature must be in Kelvin, and this is 26 degrees Celsius, so you need to add 273 to convert that to Kelvin. This is in Pascal, which is alright. So pressure is in Pascal, or it could be Newton per meter square. The volume there must be in meter cube. The mass there must be in gram, because the unit of the MR is going to be gram per mole. So we have the mass of the flask containing the air, and we have the mass of the flask containing Y here. So what is going to be the mass of, let's see, we need to first work out the mass of the air first, I think, because the density of air is there. So what you're going to do is, you have density equal to mass over volume. So what is the mass of air? So mass of air is going to be density times volume. So 0.00118, that is gram per cm cube for the air, multiplied by the volume of the container, and you're going to get 0.118 gram. Okay, so that is the mass of the air. In terms of what happened next, you need to take away the mass of air from the mass of the flask, because this thing here, the mass of the flask containing Y, is going to contain the air as well. So what's going to happen is, no, cannot be. If you read the question, this is, first of all, you fill it with air, and then you fill it with another gas Y. So I need to find what is the mass of the flask first, because I know the mass of air already. I need to find the mass of flask. So the mass of flask is going to be the difference. The mass of flask is going to be number 1 minus this thing here. So it's going to be 47.9, what am I doing here? 930 minus 0.118 gram for the air. So what I get is 47.812 gram. Running out of space here. I wonder whether I can squeeze my working down. Part 3, so the mass of Y is going to be the difference between the mass of flask containing Y minus the mass of the empty flask step. So 47.989, that's the mass of the flask plus Y minus the mass of the empty flask, and this is going to give me 47.812, so 0.177 gram. So having done all that, I think we are ready to sub in a few things, and then we can get cracking with our calculation, which is PV equal to nRT kind of calculation. I guess the difficult bit is really working out the mass of the gas Y there. Okay, let me just change the color so that we are not easily confused at what we need to do from this point onward. Now what else do we have? We have the volume of the container, which is 100 cm cube. So a lot of students have problem converting cm cube to meter cube. I never really memorized the conversion factor, because I know I could do primary school mathematics, where 1 cm is 1 divided by 100 meter. So 1 cm is equal to 10 to the power minus 2 meter. And then I could cube both sides. So if I cube both sides, whatever I do on the left hand side, so 1 cm cube is equal to 10 to the power minus 2 meter cube. So therefore, 1 cm cube is going to be equal to 10 to the power minus 6 meter cube. So whatever is in cm cube, I just multiply by 10 to the minus 6. I could convert that to meter cube very, very easily. This thing, plus 273, will convert that to Kelvin. This is already in Pascal. So I'm all set to just plug into the formula. MR equal to the mass. Mass of what? The mass of the gas in gram, because all of this belongs to the gases. Since this is an ideal gas equation, everything in here, mass of the gas, temperature of the gas, volume of the gas, pressure of the gas. So be very careful, it's for the gas because it's an ideal gas equation after all. R is at 0.31 joule per Kelvin per gram, and then the temperature is 26 plus 273. So should have done that on my calculator earlier. So there's 299 Kelvin. So I'm just going to multiply by 299 Kelvin. And then this is divided by PV. So the P is 1.00 times 10 to the 5 Pascal. And what do I have for the V? Is 100 cm cube. Converting cm cube to meter cube times 10 to the power minus 6. Now it's time to press your calculator after you have gotten everything set up properly. Hang on, divided by 100 and times 10 to the minus 6. So what I get is 43.979. They didn't ask us how many significant figure to give this one to. If you look at the data, this is 1, 2, 3, but this one has got a lot of significant figure, too many significant figures, but this one is also 3 significant figure. For the pressure, I would say 3 significant figure based on the data is appropriate. So I'm just going to run this up to 3 significant figure. This has a unit of gram per mole. If you don't like that gram per mole, you can use gram mole minus 1. I don't think they'll penalize you for the unit, but I guess, you know, it never hurts to actually know that the proper unit for MR is gram per mole there. So in this next part of the question, why is nitrogen very unreactive? We know this is down to the very strong nitrogen-nitrogen triple bond that needs to be broken down, and as such it has very high activation energy before the reaction could even get started. So this is very strong nitrogen-nitrogen triple bond, triple covalent bond. If you have these data of the bond strength, the bond energy from the data booklet, you should really quote the value. But I understand that in the latest newest syllabus that the data booklet is no longer provided in this paper 2 setting. Instead, what you have is you have a list of data that will be accompanied inside the question paper itself. That is per the 2022 A-level Cambridge International syllabus onwards. So very strong nitrogen-nitrogen triple covalent bonds need to be broken before they can react. That is the reason why the reaction will have very high activation energy and therefore very slow and very difficult to initiate. Now, as for the next question, why are the conditions inside a car engine then? Why is that suitable, or why would that result in the production of oxides of nitrogen? Based on what we have said earlier, you do need to break this nitrogen-nitrogen strong triple bond. So inside the car engine, so we are combusting, we are doing combustion of fuel. So this combustion of fossil fuels, well, I guess I don't want to generalize it with fossil fuels because you could be, you know, using a fuel cell or something, but essentially you are consuming fuels. So this combustion of fuels produce or release a large amount of heat energy, and this is sufficient to break the nitrogen-nitrogen triple covalent bond, allowing the N2 to react with oxygen in the air. So you have O2 that's present in the air in about 21%, and you already have 78% of nitrogen in a dry air to begin with. Now give an equation, meaning one equation, for how you're going to remove the nitrogen monoxide, so that is NO, from a car exhaust in the catalytic converter. So what the NO is going to do is it's going to react with CO, and these are dirty, basically pollutant and pollutant. And what we're going to do is we're going to form CO2, so the CO steals away the oxygen. Basically, the CO gain the oxygen from the NO, the CO get oxidized to form CO2, and then the NO loses the oxygen and you will get N2. Of course, we know better than to leave any equation unbalanced. Having done A-level, you should know that you can use fractions. If you really don't like to use the fractions, you can have the whole thing multiplied by 2. Then you get 2NO plus 2CO and 2CO2 plus N2. Just like that, you get a 1 mark down there. Okay. In this equation, you also have the use of a catalytic converter. So the typical catalysts like rhodium, palladium, platinum catalysts. Now these are transition metal as a solid as the metal itself. So these catalysts are in a different state as these gases in the catalytic converter, passing through the catalytic converter, and therefore this is going to be a heterogeneous. I was about to say homogeneous, but they are in a different phase or different state as the reactants there. So that's why they are called heterogeneous catalysts, and these are one of the few definitions inside the AS rate of reaction topic. Now the last bit of this whole question, one of the main reasons for reducing the amount of oxide of nitrogen is due to the fact that they can form acid rain. We know these are oxides of non-metal, including oxide of nitrogen, oxides of sulfur that can result in acid rain. We're going to form nitric acid. So you form nitric acid from NO2. This can be a difficult equation to write if you don't know what you're looking for. So what we have is NO2 dissolved in water, and you get HNO3, that is nitric acid. But whatever you try and do, you will not be able to balance the equation unless you know the other product. The other product is actually going to be HNO2. So in order to balance this equation, you really need to know that this is one of the classic disproportionation reactions. So you have learned a couple of classic, especially the one involving chlorine and NaOH. But this is one of the disproportionation reactions involved in the formation of acid rain directly from NO2. This is nitrogen plus 4 oxidation number. Since each of the oxygen is -2, you get 2 of the -2, so the nitrogen is +4, giving the overall oxidation state of the molecule, the compound having 0 oxidation number. When you have HNO3, what essentially you have is 0 for the overall molecule, 0 for the overall compound, +1 for the one hydrogen, and then the nitrogen is what you want to find. You have 3 oxygen, each of which is -2. The nitrogen there is going to be +5. So we have a nitrogen +5, and now you have HNO2, which you will learn as HONO, or HNO2 is basically the same as HONO. The name is called nitrous oxide. You will use this in A2 benzene chemistry. So what we have is 0 for the overall compound, and then you have +1 for the one hydrogen. Nitrogen is what you want to find, 2 oxygen, each oxygen of which has a oxidation number -2 in the compound there. So that's going to give you +4 - 1, that's +3. As you could see, changes in oxidation number, the +4 there going to +5 is an increase of 1, the +4 there going to +3 is a decrease of 1. Changes in oxidation number has to be balanced out. In this case, they are balanced out. This is a redox reaction. That's why I say if you don't know the other product, it's almost likely that you won't be able to balance this equation easily. There are 2 nitrogen here, so I need 2 nitrogen there, and what I have there is 2 times 2, 4 oxygen, plus 1 oxygen is 5 oxygen, and 2 hydrogen, 1 and 2 hydrogen, 3 and 2, 5 oxygen there. Now, speaking of which, this very last equation is another very important case study. This is about the catalytic role now of the NO. The NO is acting as a catalyst to oxidize the atmospheric SO2. We know SO2 can go to SO3 in industry. Those are man-made SO3. Those are man-made H2SO4 coming from the man-made SO3. But this is happening in the upper atmosphere. This is natural oxidation. So the NO plus the SO2 is another classic, not disproportionation, but this is a classic environmental chemistry equation that you need to know how to write. This will give you SO3 as well as, am I correct? Oh, yep, the SO2 steals away the, no, that doesn't look right. No, that doesn't look right at all. It's actually supposed to be NO2. So what actually happened is the NO reacts with O2 first. So the NO reacts with O2, and that gave me NO2. And having said that, I need to balance my equation. I can have half there, or I can have 2NO plus 1 O2, giving you 2NO2. I was playing around with the earlier equation because I was looking around for the oxygen, because I know it will form SO3. So that means the SO2 has to steal away the oxygen from the NO2. If I started from NO, then there's only one oxygen to be lost and I wouldn't be forming back the NO2. So I knew I was wrong. The SO2 has to steal away the oxygen. Now I have one extra oxygen. I become SO3. The NO2 loses one oxygen. That is reduction there. This is gaining oxygen. This is oxidation there. Now what happened then with the SO3? Well, they don't actually ask us for how the SO3 form acid rain. They just want us to oxidize the SO2 to SO3. But typically, when it's a 3-mark essay question, in terms of the equation, the SO3 can react with the rainwater and you will get H2SO4. So this is going to be your acid rain, which is acidic, and this is going to be your rainwater, in which the SO3 which you just produced can dissolve in order to give you the acid rain. Of course, a few dangers of acid rain: to make river water acidic, they kill plants, they kill animals, and they can damage limestone building as well. So quite a huge amount of marks for this inorganic chemistry that we've done so far. Not just inorganic chemistry really. So we started from a little bit of physical, some ideal gas questions, some Boyle's law, but then you move on to environmental chemistry fairly quickly there.